Hi all, this is Aravind Sekar, Director of Engineering at Twilio. I have over 2 decades building and scaling distributed systems, and today we're going to talk a little bit about reliability, specifically AI-powered reliability. Without further ado, let's get into it. Reliability these days is a fundamental business requirement. It directly impacts a company's bottom line. Imagine this. What will happen in the US if 911 emergency services is not available for a few hours? Sounds disastrous, right? Yep. That is the case because today we are all reliant on these kind of systems being available all the time. And it's a reasonable expectation for us to expect the services that we use to be up and available and reliable. That goes same for any software that's out there that's serving customers. Reliability equals business continuity. It is estimated that on an average, a minute of downtime is equivalent to about $5,600 of revenue loss. So with extended outages, you can imagine what would happen. We saw what happened on October 20th, when there was an AWS outage in US East 1. It is estimated that this outage itself impacted millions of customers, causing tens of millions of dollars of revenue impact across the globe. So when systems fail, conversions drop, customers lose trust, and competitors gain advantage. So it is imperative that reliability is an absolute need across all systems. The reliability crisis. So over the last 10, 15 years, we've seen the advent of microservices architectures crawling up. So we started creating a bunch of microservices. We started breaking down monoliths. And with that, what happened was the complexity of dependencies grew as we created more services. Also, with that, what happened was that an impact or a downtime or an outage in one of these services, the impact cascaded along and it would cause widespread outages somewhere else. Also, we pride ourselves over the years in increasing the number of deployments that we've had. So previously, we used to have 1 or 2 deployments a month, or maybe even a quarter. And these days, we're doing multiple deployments in a day. When the number of deployments increase, the potential of vulnerabilities that go into production also increase. So we are living in this kind of a crisis today, where the number of systems, microservices that we maintain have increased. The scale at which we operate has increased. The number of deployments that we have per day, that has increased. And the interdependencies between systems have also increased. So how do we maintain these kind of systems today, right? We have a set of monitors that we have set up, right? All systems have typically monitors. And these monitors are threshold based. For example, you would alert someone if the number of 5x's that a system that an API throws goes beyond a threshold, or if the CPU spikes beyond a certain percentage, you alert something. Same thing with a heap, or you have different thresholds that we set up for each of these monitors. That's one way. The second thing is when these thresholds are broken through these monitors, we start alerting people. But what happens whenever there is a bigger outage, when you say an entire region goes down or a full system goes down due to some infrastructure issues or networking issues, the number of alerts that we get from each of these monitors is humongous. Say I'm on call and there is an outage that's happening in a region that we have deployed code. And each of these hosts that have these monitors, the thresholds are broken, monitors are triggered, and I start getting alerts. And I would be getting like 100, 200,000 alerts at the same time. So what would I do at that point in time? Which one should I look and which one should I not look? And that's called an alert storm. An alert storm is disastrous when you're on call because you will know what to prioritize and what not to prioritize. Root cause analysis, right? So root cause analysis, with the amount of telemetry that we have today, some companies emit billions, multiple billions, sometimes even trillions of transactions every day. And how do we analyze all this data that's out there? That's a tremendous amount of data that we emit these days, and analyzing them to even identify the root cause analysis, matching data across these systems becomes a nightmare. Knowledge silos. So when these systems expand, as systems grow, the knowledge that we have inherently is not usually documented across and not documented in a standard format. So these things stick into people's minds, and then when people leave, the knowledge goes away. The on-call burnout. So we keep firefighting. Whenever there are system outages, we have these huge alert storms that come in. We keep firefighting, we keep looking, because we are not sure where the outage is because of too many alerts that come in, and firefighting becomes a norm. We don't look at how do we prevent issues, we look at how do we resolve issues once they occur. So that is the current state, and these are huge limitations in the way we handle, support these scale systems. AI is being seen as a panacea for everything, but here we should be careful as to how we use AI in AI operations. So wherever we use AI in operations, while we maintain these large systems, it's called AIOps. Now, where can AI help us? So AI can help us, or ML can help us in pattern detection, right? Something has happened before, and if the same pattern happens again, ML can help us detect those patterns, right? For example, if during the holidays, see that the number of requests that an API gets or the system gets increases during holidays, then that's a pattern, and it happens every year during the holiday. These patterns are detected automatically by ML, and we can definitely use ML models to identify these patterns. Then comes predictive analytics. So once we know there are these patterns that are available, we can also start predicting using ML models when an event can reoccur or when an event is going to occur. And we can start alerting people saying that, hey, there is an event that's going to happen, and let's take care of that before the event actually happens. The next one is intelligent automation. So if you've already predicted that something is going to happen, or if you've seen the remediation steps that we've already taken when these kind of issues have happened in the past, we can automatically start executing those remediation steps using ML models. And insights, augmented intelligence. So insights, so with the large number of data that we get out of, say, telemetry, logs, etc., events, etc., instead of analyzing all this data manually, ML models can definitely help us there. We'll go a little deeper into this. The reliability framework, right, that's based on ML and AI. So it all starts with anomaly detection. So how does that work? You have data that's coming out from systems, and this data could be telemetry data, could be events, could be logs, could be anything that's coming out. And bringing all that data together and analyzing them to find anomalies is what ML can do. So that's the first step, finding anomalies from all the data that's coming out. Second step is temporal seasonal awareness. So these models, when they are fed with seasonal awareness, in the sense all the holidays that are coming up, say during the Super Bowl match, the number of pizza orders could go up. So that is something that's seasonal. So you know that, okay, there is a Super Bowl match that's going to happen this weekend, and I know that the number of requests hitting my API is going to go high. And that is also an input to ML, and the ML models are going to use that to predict what traffic patterns across the days. Cross-signal correlation. As we discussed before, metrics, logs, traces, these are all different data. Now bringing them all together and finding patterns across this data is imperative, and ML can help us do that. Causality over correlation, cause and effect. Right? So we know, so today what happens is humans are the only ones who can find out this happened, and an incident happened, and this was the root cause, and we are able to do that after a lot of analysis. But ML models can do that when they have all the data. So a primitive approach to this would be, okay, I have an incident that's going on, another incident in another organization, or say in AWS or any other company that I'm reliant on is happening, so I can relate them. So that is a primitive idea. But beyond that, ML can identify root causes, not just based on coincident events. It can go much more deeper than that. And continuous adoption. Systems automatically adjust as applications and workloads evolve. So how do we build this for our systems? The first step to use AI for reliable operations is streaming telemetry. Telemetry is important. Real-time collection of metrics, logs, distributed traces is super critical. If you're not doing that today, the first step in having a reliable system and doing that through AI is to stream the right telemetry, to have the right telemetry output. Then once you have this data being emitted out of the system, you could implement or deploy ML models that would analyze streaming data. And doesn't mean that you have to deploy heavy models to analyze the streaming data. You could be lightweight models and you could keep it tiered. So at first step, you analyze this data using lightweight models and then aggregate that data and then use heavyweight models to predict, to do predictions, to do anomaly detections, etc. So it could be a layered approach. But all this inference that we're getting out should be near real time. You cannot have an event that happens now and then have these models run in the background, and then after 20 minutes or 30 minutes, you have a prediction or you have a detection of an anomaly, and then you start alerting people. That is not a useful thing. So you should have near real-time inference of what's happening in these systems. Model performance. So imagine, right, you have fraud detection in credit cards. This is one of the common use cases for ML models. You deploy ML models to identify a fraud in a credit card transaction. Imagine using the same model that we developed 10 years ago. It's not going to work today because the ways in which fraud happen in credit cards have changed over time. So we have to keep updating these models, and that's what this means. And the same thing applies everywhere. So continuous validation ensures model accuracy as systems and data systems and data distributions evolve. And you should have safe rollback mechanisms that we're seeing more false positives. Then there should be an easy way or mechanism to roll back our model and deploy older ones for better safety. So overall, we should balance real-time responsiveness with computational efficiency. Moving on, another area where you can have a very good bang for the buck using AIOps is capacity management. Say, as an example, let's take the same example of a Super Bowl match. You know that a Super Bowl match is going to happen, or you know that the holidays are coming up, you know that the traffic is going to increase to your service. What we do, we typically scale up our services, scale up the number of flows, number of pods that we have, and handle the traffic accordingly. How many of us are guilty of scaling too much during these periods and keep them scaled up because we don't know what kind of traffic is going to hit us? And even though our systems are highly scalable, they can scale whenever there is an increase in traffic. The scalability doesn't happen immediately. It takes a few minutes for any host to boot up. So it doesn't mean that you have, say, 1,000 hosts now, and the next second you're going to have 2,000 hosts. It doesn't happen like that. It takes time for us to scale up. And during that time, when we are scaling up, customers may see issues in terms of latency, availability, etc., which is not acceptable. So AI can predict when we need to scale up and preemptively scale up when required. Just in time, it's like just-in-time scaling up, but with a good sense of when it is needed and how much scaling is needed. 92% SLO adherence is basically what this means here is that by doing this, by using AI, we can adhere to SLOs 92% of the time as we scale up systems preemptively using AI. Similarly, cost reduction. As I said before, I'm guilty of having scaled up systems, having doubled the capacity, and having it scaled up without scaling down, even before for quite a number of days when it was not even required. So just-in-time scaling would reduce the cost by 35%. So super important. This is a very important place where AI can be used in scaling systems. Moving on, smarter detection and root cause analysis. The first step is always anomaly detection, right? ML identifies deviations from normal behavior. So I'll give you an example. You deploy a new version of software and you divert 1% or 10% of your traffic to the new version. Now the question is, how is the new version working when compared to the previous version? You cannot expose 100% of your customers to the new version without knowing how it's performing. So you divert a percentage of the traffic, but you have to also analyze how it is working compared to the previous version. ML models can help us do that. It can analyze how the old version is working compared to the new version and tell you what the differences are. Signal correlation, again, ML models can analyze related anomalies across services, logs, traces, etc. So it doesn't have to be just your logs or just your trace. It can do anomaly detection across services, logs, traces, etc. Dependency mapping, real-time topology understanding shows how issues propagate through the system. So when we have hundreds of thousands of microservices supporting in the backend, ML models can help you trace the issue, and it will also tell you how issues are propagating through the system. Blast radius analysis. So when we do root cause analysis after incidents, or even for during design, it is always important for us to reduce the blast radius in case of an incident. So ML models can help us quickly identify which services and users are affected by an incident, and also will help us in designing good systems where whenever there is an outage, which will reduce the blast radius. Root cause identification, to be honest, is in the nascent stage now, but I think once the data that we provide to these models are good enough, then root cause analysis or root cause identification is something that ML models can definitely help us get better at. All these things reduce MTTI. MTTI is mean time to identify, basically identifying that there is an issue going on so that we can do remediation quickly. Going to autonomous remediation. So now assume that you're using AI to identify that an issue is going on, right? We have these anomaly detections, etc. And now you know that there is an issue going on. So what should the system do? Ideally, it would page an on-call engineer, and the on-call engineer would say, okay, something is happening, let me go fix it. And how does fixing happen? We can use generic mitigations like Google has mentioned in their SRE book. There are a few generic mitigations that you could do. You can roll back a code, deploy, see if there was a deployment that happened, roll it back, see if there was a bad host, replace the host, or take it out of load balancer. So there are a few things that you could do, limit the traffic, etc., etc. So we know that generic mitigations can quickly fix an issue without much thought. Now, when we know that there are only a set of generic mitigations that can happen, the question is, can that be automated as well? So you know that an issue is going on, can we have automated systems that would resolve these issues as well, that will fix these issues? But the question is, who can we trust ML systems to make the decision of executing these remediations or not? And that's an evolving process. So one step is, you've identified the problem, you can use generic mitigations to fix these problems, and ML models here can give us a recommendation for what kind of generic mitigations to use. Once we are comfortable with that, then we can allow AI to execute these generic mitigations without even paging it. Human AI collaboration model. That's what this is. The AI suggests what kind of remediation a human should do. The human would validate that. For example, if the AI suggests, okay, there is a high number of 5xx's that are coming out of this new version of code, I would suggest you roll back the code. Roll back a deployment that happened 1 hour ago. And humans say, okay, yeah, this makes sense, let me do that. Or they can say, okay, AI would give the key to the AI and say, yep, you execute the rollback, the AI executes the rollback. And all that knowledge is captured, becomes a loop, and the AI slowly learns, yep, whenever this kind of issue happens, you can do a rollback of code if there was a deployment. So that whole cycle keeps repeating till the humans can move out of the loop and AI makes decisions automatically. Things like the future, there are advanced anomaly detections here, where the anomaly detection comes through various different sources into a single powerful representation. Also, we are seeing that models are very good at, even when ML models are dependent on past data. right? And a large number of events that happened in the past to predict the future. But we are seeing that few short learning is also happening. What that means is that even the rarest and the most elusive failure modes are also being predicted with these ML models, and that is really coming up these days. Moving on, right? What is the overall impact? Personally, I have seen a huge impact in a few areas, right? The first one is noise reduction. Let me give you an example. For example, if you're using, each company uses different tools for monitoring, alerting, ticket management, etc., etc. You may be using a bunch of tools, say, for example, Datadog or Big Panda, Dynatrace, Splunk, or PagerDuty. No matter what the tools are, all these tools are bringing in AI operations into the mix. And one of the things that we did was that we saw huge pager noise. And as I mentioned before, an outage would would break the threshold of a bunch of monitors, and all those monitors would send out alerts to the on-call person. And for every incident, there would be hundreds of pages that would reach the on-call person. And the pager storm would cause more confusion than anything else. So what we did was PagerDuty had a feature to group these alerts into one, so that the on-call person doesn't receive as many alerts, and it would intelligently group similar alerts into one alert and say, okay, I'm seeing a bunch of monitors failing. Here is one alert for you, and you may want to look into this area. And that has really helped us in reducing noise and alert fatigue and alert storms by 60%, which is huge. So when an incident these days happens, the number of pages that an on-call engineer has reduced so much. Now the on-call engineer can go and focus on what really matters, and not focus on acknowledging these pages. We are also seeing a huge reduction in MTTR. MTTR is mean time to resolution. Basically, when an incident is opened, the time it takes to resolve the incident, to resolve the issue, has reduced a lot, because with these tools are able to correlate data between these different data sources, like telemetry data, traces, logs, etc., and is able to narrow down on the area of impact. So that is really helping all-call engineers to quickly go and identify the areas where the problem is happening and mitigate the issue. As that, alert fatigue is one thing, and then incident frequencies definitely decreased number of incidents, because we are able to automate the remediation process. Nobody gets, imagine this, right? You're running tens of thousands of servers, and every time there is a CPU breach or a host goes down, if an on-call engineer gets paged just to replace the host, then the on-call engineer would never be able to sleep, right? So these things are handled automatically these days, and it's become a norm. So the number of incidents have gone down as well. And the efficiency of infrastructure, we are seeing slow progress in these things, because for better capacity planning, I see not all companies are using AI to predict capacity, but I see a big trend in large companies that are using AI to predict capacity and using that to scale systems. So definitely using AI in the real world is pretty impactful to business. So what do we do? What do we do to adopt this? Visibility and anomaly detection is phase one. So you cannot say a company that has not implemented any of these things, it's very difficult to do all these things on day one. So what you do is do this in phases, right? The first step is to emit the right telemetry data. So as long as you have data, the right telemetry data that you emit, that should help in AIOps. So if you're not emitting the right data, start emitting the right data. That is step number one. Step number two is use AI to correlate all this data and build the dependency mapping and reduce the investigation time. You don't have to do this all by yourself. There are these tools that will help you do all these things. And most tools that you use, as I mentioned before, have got these features built in these days. And all you have to do is to start using them. Automation and prediction, enabling autonomous remediation for known issues. That is step phase 3, because as I said before, you cannot rely on AI to make the decisions on your behalf. You can coach it. So slowly you can ask it to recommend what what could be a good remediation. We can give it feedback. Yep, this is good, this is bad, etc. And slowly to learn, and we'll get to a stage where it can take decisions on your behalf for the remediation as well. And optimization and scale. So expand the scope of optimization would be phase number 4. So first thing is the quality of data. Make sure that phase 1 is good. Other things would fall in place. We're coming to the end here. So key takeaways. Reliability is a given. We expect reliability from all the systems around us. And reliability is dependent on data. So if you've not done this, emit the right data, and AI can help you with reliability. And AI can go to an extent where it can help in prediction, not just reaction. So as humans, we are reactive, but humans plus AI, we can make predictions, not just be reactive. Humans plus AI outperform either low, right? So humans alone or AI alone cannot work. Humans and AI together would outperform, what humans did all these years. And what's going to happen in the future? Reinforcement learning is a big thing. Self-improving remediation policies, as I said before. As you teach AI for remediation, the number of pages that an on-call engineer receives would drastically go down, because AI will be able to make decisions on what remediation steps to take and execute them automatically. Digital twins, deployments. You would have a virtual environment which would be validated by AI, and then AI will tell you, yep, this is good, and then move that to the customers. And causal reasoning, cause and effect. So when there is a cause in one area, it's going to tell you what's going to happen, how it's going to affect another area. So these are things that are upcoming and would help companies support the systems better. So predictive prevention is the new SRE standard. I hope you all love this session. Thank you so much. You'll have a good one. Cheers.